Hello student, I am Latif sir. Today I'll discuss about ISC class 12 chemistry. The topic is solid state. The solid state. On this topic, I have already uploaded three videos. Today I'll discuss about Bragg's equation. Bragg's equation is related with crystalline structure of crystalline substance. When X-ray are incident upon a crystalline sample, they are scattered by the atoms or particles present in the system. Here you can see the diagram. It is showing that the reflection of X-ray by the particles present at the surface of crystalline substance. Here I have taken two lines or two planes of a crystalline substance. The planes are WV and XY, and the particle present along this plane. Huh. Here one particles it is shown that one particles at point B and one particles at point B dash of two different planes. Now X-rays are in X-ray incident on the plane, on both the plane. Suppose an X-ray of wavelength lambda hits an atom at B in one plane WV of the crystal at an angle theta. It will be reflected at the same angle theta according to the law of reflection. Then suppose another ray hits an atom at B dash, you have to remember now, in another plane xy at the same angle theta and reflected at the same angle, that is theta. Now one assumption you have to remember, there will be no phase difference, that is both incident and scattered rays will be in the same phase. When they will be same phase, if the path difference, that is path difference here according to the diagram or drawing or figure, you can see here the path difference is, that is extra path covered by the incident ray A dash B dash. Hmm. So extra path covered by the incident ray A dash B dash is the path difference. So path difference is P B dash and B dash Q. So path difference is P B dash plus B dash Q. Extra path covered by incident ray A dash B dash, and then it will be reflected along B dash C dash. Now if the difference or distance between two planes are d, if the distance between two plane WP and XY is taken d, small d, then the extra path, that is P B dash and B dash Q, will be d sine theta plus d sine theta. That is P B dash. Here you can see the angle P B B dash angle is theta and B dash B Q is also theta. Hmm. So P B dash is equal to B dash Q is equal to d sine theta. So total path difference is d sine theta plus d sine theta is equal to 2d sine theta. Here you have to remember that d is the difference between distance between two planes. Now according to the assumption, there will be no phase difference if the path difference is 2d sine theta. Path difference for the two rays is an integral multiple of their wavelength. Here the wavelength of X-ray is lambda. So so 2d sine theta is equal to n lambda, where n is an integer. Hmm. Thus for a consecutive interference means there will be a high intense reflection, and both reflected and scattered rays and incident ray are in the same phase. Huh. Then you can show that 2d sine theta is equal to n lambda. That is path difference is integral multiple of wavelength. Here n is the constant, n is an integer. That is, you have to remember the relation. 2d sine theta is equal to n lambda, where d is the distance between the two planes, theta is the angle of incidence, and n is a constant, and lambda is wavelength of X-ray. Now, imperfection in crystalline solid, imperfection or defect, it's sometimes called defect in crystalline solid. Defects means irregularity in crystalline structure. Okay, so in, let's say, imperfection in crystalline solids. In a crystalline solid, the particles or atoms or ions and molecules are arranged in a definite repeating pattern. But some defects may occur in the pattern. Deviations from perfect arrangement may occur due to the rapid cooling or due to the presence of particles. The defects are of two types, namely point defects and line defects. First, point defects. Point defects are the irregularity or deviation from the ideal arrangement around a point or an atom in a crystalline substance. Point defects can be classified into three types: stoichiometric defects, impurity defects, and non-stoichiometric defect. Today I will discuss about stoichiometric defect. Stoichiometric defects are point defects that do not disturb the stoichiometric of the solid. That is, stoichiometric means the number of cations and anion will be same. Okay, that is, there is, their composition will be same after this defect. Okay. Stoichiometric defects are point defects that do not disturb the stoichiometric of the solid. They are also called intrinsic or thermodynamics defects. In ionic solids, basically these are of two types: Frankel defects and Schottky defect. So two types of stoichiometric defects are Frankel defects and Schottky defect. Let's see. Let read about this defects: stoichiometric defect, Sco- uh, Schottky defect, and Frankel defect. First, see the diagram. Here, the left side, the figure B shows, figure A is a Schottky defect and figure B is a Frankel defect. According to this diagram, it is clear that in Schottky defect, if there is a vacancy of cation from the crystal, then there will be one anion leave the crystal system. Hmm. That is vacancy of both cation and anion. But in Frankel defect, you can see cation vacancy. Then the cation will occupy the interstitial site of the crystal. Here, cation leaves their own position and goes and present at the interstitial site of the crystal system. So let's read the differences between Schottky defect and Frankel defect. Schottky defect, it is due to equal number and equal number of it is due to equal number and cation and anion missing from the lattice side. One mistake here, right? Missing of cation and equal number of cation and anions missing from the lattice side. Schottky defect is due to equal number of cations. Cations not written here. You have to write down number of cations and anions missing from their lattice side. And Frankel defects, it is due to the missing of ions, usually cation, from their lattice side, and they occupy the interstitial site. In Frankel defect, the cations occupy the interstitial site. Second point, Schottky defect. This result in the decrease in density of the crystal. This is because number of particles leaves the crystal system. The cation and both cation and anion will leave the crystal system. therefore their density will decrease. But in case of Frankel defect, there is no loss of cations from the crystal system. The cation will occupy the interstitial site, but the cation will not leave the crystal system. Okay. So in Schottky defect, there is this result in the decrease in density of the crystal, and Frankel defect, it has no effect on the density of the crystal. That is, in Frankel defect, the density of the crystal will same. Now, next one, Schottky defect. This type of defect is found in highly compounds with higher coordination number. Example: NaCl, CsCl, cesium chloride. And Frankel defect, this type of defect is found in crystal where the difference in the size of cation and anion is very large. Example is silver chloride, AgCl, ZnS, zinc sulfide, etc. So read read the take a screenshot of difference between Schottky defect and Frankel defect. AgBr, here one point is given. AgBr is a substance that has both Schottky defect and Frankel defects. Frankel defects are not found in pure alkali metal halide, because cations are of large size. Now, second point, impurity defects. Impurity defects arise when foreign atoms or ions are present in the lattice. In case of ionic compounds, the impurity is also ionic in nature when the impurity has the same charge as the host ions. Second point, impurity defects can also be introduced by adding impurity ion having different charge than host ions. Example, in molten NaCl containing a little amount of strontium chloride. Here Na sodium is Na plus and strontium is strontium 2 plus. So if Na plus leaves is its crystal site, then you can add strontium chloride, because one strontium 2 plus will occupy 2 Na plus site, will be equivalent to 2 Na plus. Okay, so impurity defect can also be introduced by adding impurity ions having different charge than host ions. Example, molten NaCl containing a little amount of strontium chloride is crystallized. Thank you.